Okay, so today we're going to be going over branch and jump instructions, and then we're going to be going over how variables are passed back and forth between functions, and then we're going to start getting into memory hierarchy. So previously I've told you there's this data memory and there's this instruction memory and there's this box there, and I've told you just press the I believe button, and starting in section 5 we're going to be going into detail into how those actually work, how you can use that to try to speed up interactions between levels of cache hierarchy, and then why we would separate registers, instruction memory, and data memory. So branches are immediate instruction types, where the 16-bit value of the 32-bit instruction is actually going to be the number of instructions you're going to branch past. So we have three types of branch instructions. We have branch if equal, branch not equal, and set less than. So branch if equal, so what that means is we want to branch past a set of instructions if the two variables we're comparing are equal. So that's an instance where if it's I does not equal j, then we do the code inside the loop. Or while I does not equal j, and we would do the code in the loop. We would branch past those instructions if I equal j. So so think of it as the opposite. Whatever you're coding in there to do the instruction, whatever it's not, you're going to do that type of branch. So branch not equal, that means we want to do the code if it's equal. Set less than, we're going to be showing examples of how to use set less than. MIPS does not have a physical implementation of branch greater than or branch less than. On the MIPS green sheet, it has something called pseudo instructions where those are listed. They are called pseudo because they are not real. What the compiler actually does is, and we'll do an example, that actually arrange a set of 2 or 3 instructions based on the specific one you're going to want. And on an exam or on an assignment, you are not permitted to use pseudo instructions. So 4.26 is jump instructions. So this is basic. It's a 6-bit opcode and then a 26-bit value indicating which instruction we're going to use. For JR and RA, if you recall from the MIPS, the RA is return address and is the 31st register. And then this is called jump and link. So what happens is it's going to copy to the program counter to register return address plus 8. So basically you have the function call, and then it's going to call two instructions afterwards, and then it's going to jump to the program. So if you are inside main and you actually want to jump to the set of code where your function is, you would use the instruction jump and link. So you're basically saying, all right, here's where I am, the function is next, and then the instruction after that is where I want to get to after I call the function. So I add 2 instructions, and I store that as my return address. And then from there, you would jump to the actual instruction. So what exactly are branching and jumping? So here's a simple C snippet. And branching means you're going to go past the code. So here we have while I equals j. So in C, this indicates that we're going to, while I is equal to j, we're going to do the code inside the loop. If we wanted to break this, if we wanted to branch past this, which one of the 3 instructions I just mentioned would we use? We want to branch past it. The semantic is important. That's why Which one? We have branch if equal, branch not equal, and we have set less than. Branch not equal. Why? Why would I say that branch if equal is wrong? So if I'm here and I say I want to branch if equal, what would happen? If you set branch if equal and then I equals j, it will go past the code. The branch is branching past. So we would want branch not equal. That means I does not equal j, then we're no longer doing the code. Does that make sense? I see some Sure. All right, where's the chalk eyes this time? Nowhere. We're out of chalk. All right, so here's a general idea. All right, that's saying, stand up. You're going to be trying to block me. You are like Gandalf, so you're going to be, I'm like a car, and you are PRTs, so you're going to be like this, right? So this is when you guys are sleeping in, this is what he's doing in the morning. Okay, so let's say, yeah, sure, because this is a good example, because you're going to be not letting me pass you as a branch example until I meet the condition. So I have to stay here inside the loop until while I equals j is no longer the case, right? So let's say, okay, so inside, I want you to stand up. So hold up your hand, and hold up a 2. So he's I am j. So right now, we're both 2. So we have to stay in the loop right now, right? So branch of equal means we branch past him if we're the same. Does that make sense? But you don't want that, right? Because we have to stay here while we're the same. Right? So we iterate, change to 3. So I change to 3. Can I branch? Okay. So change to 4. I stay. Now, we want to branch if we're not equal. So if we're not equal, then you permit us to pass. Let's go. We can branch past him, and then we do the next instruction, right? So that's how this works. Thank you both. Okay, so branching means you go past the code in the loop. Since I equals j, we execute the code and branch if I does not equal j. The current instruction is stored in the program counter, and we're going to be going examples of how this program works. There are 2 instructions in the loop, so we're going to be, but then we would compile these using the MIPS machine language instructions. So that's how we would determine the number of instructions we want to go past. So if we look at the MIPS screen sheet for branch not equal, a branch on equal, it's curious. It says if RS and RT is equal, the new value of the program counter, meaning the new instruction we're going to be at, is equal to PC plus 4 plus the branch address. Let me see if I can zoom in here. Yeah, here we go. So here we go. If it's RS is equal to RT, then, can you guys even see what I'm looking at? Yeah, you should be able to. Then PC equals PC plus 4 plus branch address. So the instruction that the value in the immediate of that, so we have the 16-bit, is equal to the number of instructions that are in the code that we want to jump past, right? So let's say we have 4 instructions. So, but here we have this curious PC plus 4 here. Why do you think we have PC plus 4? 4 is the hex. Kind of, sort of. You're on the right path, though. What do you recall that we have to do? What is the importance of the value 4 in memory calculations, especially in MIPS? Yeah, we have 32 bits, and what type of addressing do we use in MIPS? 8-bit. And what is 8 bits? Block of, what's 4? I'm looking for a different B word. Byte addressing. We have byte addressing. So we add this PC plus 4 here because it's going to jump to the next 4 blocks. That would normally just be the next instruction, because you have 8, 8, 8, 8, that becomes 32-bit instruction, right? And then the branch address here, when you compile it, it's going to have the just the number of instructions. So if we want to branch past 4, there would be 4 instructions in there, but we would get to the 5th instruction because we're adding the initial instruction here, right? But here's the thing. The value in the instruction is just the number. It is not the multiplied by 4 address. So how do you think, if we're not doing that in the code, since you guys are now in advanced digital systems, if I give you a integer in a binary value and I want it multiplied by 4, what logic structure have you designed or are in the process of doing for assignment 3 that you would insert into your data path to make this, you multiply this by 4 and then it adds correctly? Shift, do it, shift, left, there you go. And what would be the input? If I multiply by 4, how many am I multiplying by? Shift left by 2. So you have a separate SL2, and we're going to be going into this in the beginning of section 5, physically how this is done. You're going to have a unique shift left by 2, multiply this branch address, add 4, and then add it to the current program counter, and that's how we determine how many blocks we go past. So if I'm doing a branch if equal, that means if I is not equal j, and then I have 2 machine instructions, what's my value of branch? What's the value going to be in the instruction itself? If I'm branching past 2, if I want to branch past 2 instructions, what's the immediate value going to be? Oh, yeah, you. Say it out loud, you. 2, right? So it's just going to be the number in there, and then physically, what does that become? After you do the shift left logical. Go back to first grade. What is 2 times 4? 8. There we go, right? So if I have physically what's going on, if I have 2 instructions I want to branch past, the value is 2. We shift left logical. So now there are 8 blocks I want to go past. But then I want the instruction afterwards. So it's going to be 8 plus 4 plus the value we're at. Right? So we want to get past that initial instruction that we're actually doing. So that is what's physically going on here. Does that make sense? Yes? No? Anyone saying no? Okay. I don't know if y'all can hear that music that's going on outside there, but that's going to be interesting on the video. So here's the actual physical representation. So I have shift not equal 2, so then 20. And then we're going to be doing a shift by 4, so then that's going to be the instruction. So jump instructions are different. Branching just means I want to go from here to here. Jumping means I have a known address that I want to jump to, right? Branching is a conditional thing. If it meets the condition, we branch. Jumping means no matter what happens, no matter what thing is standing in front of me doing, I have a jump pass. I can go to this instruction. I can jump forward. I can jump backwards, which you're going to need to do, especially if you are in main. You go to a function call. You do a jump and link. You go to your function. You do your function. You get to your end of your function, and you have to go back here, right? Jump return address. That's what's going on. So here we have our register transfer language representation. PC is just going to be equal to jump address. So in section 5, we're going to discuss specifically how to take a 26-bit value and turn it into a 32-bit value. And so then you have your opcode and then a reduced, it should be more bits, but so going back to our original code here, this is just the while loop that we were talking about. So if we start at 64, we're jumping back to 64, right? We have this branch not equal, and we're comparing because it's while I equals j, right? So we're branching if it's not equal, and then the code.
Sorry, it just flew just right.
Oh, okay. You just went boom. I was like. back down, Wolverine. Like, so now we're doing the same thing. We're going to do a shift left logical as if A of J, right? And so we have to calculate the address and then load it into I and then increment J. So we're taking the base, taking J, we're multiplying it by 4. We're adding it by the offset of the base address of A, which we'll call S0. So now we're pointing at the value that we want, A of J. Then we load I to 0, because 0 is the offset for our pointer, for T of 0. So I is now equal to A of J. Then we use the add immediate instruction to increment, A of J. Then we increment J itself. And now J64 means I want to go back to this unique instruction here. And so the branch will actually go to whatever this instruction is. Does that make sense?
For 65 there.
Yeah. Yeah.
Does S3 contain 4?
S3 contains J.
Okay.
So this is an array. So what we're doing is we have to multiply this by 4 to account for byte addressing. And then we have to add it to the base address, and then we have to,
so the shift left logical.
Yeah, shift left logical. We're multiplying.
So that's multiplying.
Yeah, this is what this is coming. Is multiply J by 4.
Yeah.
And so here we're going to discuss what happens since we don't have branch greater than or branch less than. And the reason they did that is to reduce the size of the controller, which when you guys are coding the controller in VHDL, you'll be very grateful for. Basically what they're doing is they're having a compiler driven. So we use this set less than instruction in order to take advantage of this. So set less than, we're going to set the destination register equal to 1 if RS is less than RT. So if I have, in your MIPS 8-bit data path, if I have two 8-bit values that I want to compare, and then you have a 1 on the output, or 1 is being sent to RD, or 0 is being sent to RD, if it's not the case, then what logic structure that you have designed already are you going to use? Yes, 8-bit comparator, right? And you're going to set it specifically to less than value. So for the cases where I is less than J, because it's not a case where it is equal or it's not equal, so you have to have multiple instructions. So for topical guide objective 4.27, there are 4 unique cases here where it's going to be I less than J, I less than or equal to J, I greater than J, or I greater than or equal to J. So when I is less than J, branching if equal is not sufficient because we also have to consider the case where I is less than J. If I is equal to J, we want to branch, but we also have to consider this other case. So first thing we do is we set T0 set less than when we compare I's and J. So if I is less than J, then this value is just going to be 1. Come on, that should be branch not equal then. So then, my apologies, hold on, let me fix this. Sorry, minor mistake. Look at all the stuff you guys have already learned. And you guys. Okay, so we set less than. So if I is less than J, then it's going to be 1, right? So that means we want to do branch not equal. And the reason we want to do branch not equal is that here what we have is a case where if we meet this condition, if I is less than J, then T of 0 is going to be 1. So, and the value in register 0 is always going to be 0. Correct? So then we have our PC plus 4 plus branch address here. So that's going to then become BQ down here. Okay, so what if I is less than or equal to J? Well, first and foremost, if I is equal to J, then we definitely want to branch. What? Oh my gosh, I hate this. I is less than J. Okay, so the first thing, we want to branch if I is equal to J, we do not want to branch. So if I is not equal to Okay, so let's work this out then. Okay, so if I is, first thing we want to do is we want to check for if I is equal to J. So if I is equal to J, we don't want to branch. So I've screwed up here. So let's comment this out. And let's get rid of the automatic formatting. So we want to set less than. So if I is, I know what I made, what mistake I made. Copy and paste. So we want to set less than like before. We want branch if not equal, meaning if it's less than automatically. But then we want to account for a third thing. We also want to account for the fact that in this case we're branching if it's less than here. But we also have this case where we don't want to branch if it's equal. So, yeah, there we go. Branch not equal. S1 and S2. So we set less than here. If it's I is less than J, did I have this right the whole time and I'm just screwing it up? Not having a good morning. Okay, so if I is less than J, that means anything else. So we set less than if it's 1. That means it can be 0 if it's not less than J, which means I had it right the first time. Okay, so let me explain why I'm an idiot. All right, I have a PhD. All right, so and this is the one thing that I always get wrong and I'm always paranoid about it. If I is less than J, then what happens is we set less than S1 and S2. So if it's less than J, that means it's going to be 1, right? That means we want to do the code. So that means we want to, if it's 0, that means I is not less than J, and we want to branch. Therefore, if T0 is 0, that means I is not less than J, and therefore we need to get past the instruction, right? So the second part is I is less than or equal to J. Then the first thing we need to account for the fact that if I is greater than J, that's not sufficient. So the first thing we want to do is we want to test for set less than here. If it's less than, if I is less than J, then it's still less than or equal to J, right? So you want to branch not equal, branch of equal, right? So if it's I is less than J, we've accounted for every case here, like with these same first two instructions. But the one thing we haven't accounted for is what happens if I is equal to J, right? So we've eliminated, we think of it like a block, then we have all the values here where I is less than J, and then we have I equals J, and then we have I is greater than J over here. So these first two instructions, we've eliminated this case. So now we have to account for this case here, correct? So the last thing we need to do is we need to branch if this is not met. So we branch not equal because we want to do the code if this condition is met. And then we now only branch in that case. So my code was actually right. Here, now we have to account for if I is greater than J. So again, we compare set less than, because that's the only one we have. So if I is less than j, then we already want to branch, right? If I is less than j, that means I is not greater than j, correct? So if it's equal, if it's set less than, then we want to branch if it's not equal here, because if I is less than j, then we're going to set it to 1. And if 1 is not equal to 0, then we do not want to do the code. But in this case, we also need to account for the fact of what happens if I is equal to j. If I is equal to j, we do not want to do the code, correct? So then, branch equivalent. And last and certainly not least, if I is greater than or equal to j, we set less than. If I is less than j, then we're going to branch if equivalent, just like here. Because doing the same thing, we had the I is less than j, I is equal to j, and then I is greater than j, right? So we now have this instance where we have if set less than, so I is less than j, correct? So if it's 1, then we know it's less than. That means we want to branch past the code. So then that becomes branch not equal. So if I is less than j, that means it's not greater than or equal to j. So we've already lopped these off, right? So that's when we want to do the code. So in the only case now, we want to branch if I is less than j. So then this becomes t equals 1, and then branch not equal. Okay, does that make sense?
So you're saying, you have that 0 there?
Where?
Is that,
Yeah,
right there.
Mm-hmm.
So is that saying like branch when not equal to 0?
Correct. So here we actually, if you recall from our register names, we actually have a dedicated register 0. So what's going to happen in this last case, if I is less than j, and it's going to be done in this order because that's what the coder has done, right? If I is less than j, then it'll be 1.
If that statement's true.
If that statement's true, then it'll be 1. And then we'll set this value to be 1, t0.
Mm-hmm.
And if they're not equal, that means that I is in fact less than j, and therefore we want to branch. So we use this because, if you recall from the instruction types, we have opcode for I type, then RS and RT. So we have 2 registers. We can't, and the immediate value has to be the branch instruction. So we can't store just another value in there, another integer. We actually have to have a value from a register. That's why we have a dedicated 0 register. Any other questions about this? Okay, so with instructions in a function, we have v0 and v1. So if you look at our MIPS screen sheet here, v0 and v1 are values for function results. So if you've done like int, funct, and then you pass some variables, that integer or return values could be v0 or v1. A0 through A3 are variables that are passed to the function. And RA is the return address from that function. So let's break down how this is done in C code, what's physically going on when you actually call a function. So I've given an example here of what I call while. Hold on, let me save as. Yeah. I'm going to do save as PDF because that way I can get rid of all the spell check stuff. Okay, so we have this C function. So first, let's go down to main. So I've kind of initiated some variables, and I have a array of integers, right? And I've memory allocated these integers such that I have an array of size 40, and I is 20, so I is going to be half of 20. So for k through 0 through k is j divided by 2, which I could have put I there and would have been fine. Vowels of k is equal to 0. So the first 20 elements of the array are 0. Then the next 20 elements, all the way up to k, there's going to be j times k. So it's going to be 40 times whatever the value of k is, and that's what's going to be stored in the array. And then I printed out the values before, and I printed out the sum. So I have this integer sum, which is just I plus j. And then I print out j before the function. Now the reason why is because in the function itself, I pass the integer array, the base pointer of the array, to the function. I pass int I by value. I pass int j by value. And then int star sum is a pointer to the value of the integer sum. So we have the base pointer of the array being passed here, and we have the base pointer here. So if we were differentiating that, we would have temporary registers, which we could use as physical pointers to the data we want. And then for int I and int j, we would use those registers, if you recall from the MIPS screen sheet, A0 through A3. Those are arguments for the register. So we're passing by value. Now the thing is, once you're done with that, in main, you're not going to call those anymore. So if you recall from when you're doing C or C sharp, C or C++ coding, and you pass by value and that value is gone in the register, that's because it's accessing the registers that are only available to main and not the arguments themselves. Because the moment you're done with that code, just like temporary registers, you can overwrite the argument registers. And so inside here, I have a loop where I add the value of the sum. So here, see the star sum. If you've done C coding, remember it'll tell you that pointer is incorrect if you don't have the star in front of it. So here's what's physically going on. You've passed the pointer, what we're pointing to in memory, right? So if you just add the array value to the pointer, you're not changing the value of sum, right? You're changing where it's pointing to in the data memory. So that's why it won't let you do it. The compiler will say, no, that's bad. So what you have to do is you have to do a load word instruction, pull the value in, perform the operation on a temporary register, and then if you're updating it, like here on sum plus equals vals in the last instruction in the loop, you have to perform a store word operation. So by doing that, that's how you do pass by reference, because we're referencing its location in data memory. And then here we have I++, since it's passed by value in one of these argument registers. When we call I or call j in main, it's still going to be the registers that are passed there. So you're not going to have the updated values. So I run the code, and then after I do my function call, here, return value, because while function, I pass these values here. What's going to happen is the return value is that v0 integer, so I'm returning I plus equals the last vowels. So this would be an integer that is returned. So that's going to be register v0. That can be read in main. So this function here is actually this %d. It means print integer and fprint out. And then here I have a number of other values where I'm actually checking the updated copies. So I compiled. I like the GCC compiler. I think it's a very good compiler, and here's a link for it to download if you want to mess around and test these out when you're studying. And so these flags here in my compiling, wall just enables all C compiler warnings. ANSI enforces the ANSI-C standard. So this O flag links the generated output file to test. And then this instruction next is I'm actually running the output file. So it's actually going to run the code executable based on that. So as I expected before, the first half are all zeros, and then I have 800, 840, 880 because I multiplied j times k. Sum before is I plus j, so it's 40 plus 20 is 60, and then as we know, j is 40. So I'm running the sum value, and we can see sum is returned in variable v0. So as a result, that V0 is going to be returned back here and is printed out. And J inside the function, since we've decremented J by I, is now 20. So this value right here that's being printed out is inside our function call. So that's the A0 being printed out. The updated value of J that we've passed by value. So now we're back. So these print values were back into main. So I've returned our sum value of 820. Our return value is 820. So if I do return value here, so that's the value we've returned, sum before function. And if recall, at the end here, I returned I plus equals vals of I. So I is 20, right? So this loop keeps going until it hits I does not equal J, which means it's not equal to 0. So it got halfway through here, and it got to the first element, which in this case was 800. So it added 20, and we got 820. So that's why it's the return value. But now it's been updating the values of the array inside the function. And since we passed the variable, the pointer to the variable, with the base pointer of the array, we are actually physically changing the copy of the array. If you did something where it was like int vals, and then you had the two brackets afterwards, you would actually have been passing the array by value. So you would not, if you did that, you would get these initial values. So that's what's physically going on with the array. The sum has been updated in the function, and since we have it as a pointer, and we've been loading and storing, when we get back into main, we update that pointer by loading that value from data memory and putting it back to the local register that we have. So that's why this is updated. But here's the thing, J was passed by value, and since we're referencing the original register, it didn't change. So J before function and J after the function are the same. So that's how all of these pointers are physically working. Does that make sense? Awesome. And basically all of this is what I've just explained to you. So in MIPS, we pass by value by using registers A0 through A3. We pass by reference by passing a pointer to the base address using a temporary register. And then the value returned by the function is stored in V0 or V1. So we're now going to do a smaller example here in 4.12 to actually show what's physically going on in a C code at the MIPS level. So now you're going to take that and show me using the MIPS assembly language that you know what's physically going on in C. So we have this function called while function where we have the pointer to an array of vowels. Vowels is an array of words located in memory. I is A0 because we are passing by value. Int star sum is the pointer and it's T of 0. J is an A of 1, so we're passing that by value. And the base address of the array of vowels is in T1. So it's there. So now we're doing a while loop. So if vowels does not equal 0, then if I is less than or equal to J, we're going to update sum with our pointer to vowels. And then we're going to increment I, and then we'll return this just like before. So let's do step by step through the code, what's going on here. So the first thing we got to do is we actually have to get the value of I from vowels. So as I indicated in the problem, the first instruction of the while loop is 256. And this becomes important because at the end of the while loop, we need to jump back to 256. And then the last portion, return address is stored in RA. Since we're going to be doing a function, if I do something like this on an exam, the last instruction you need to write, you need to actually leave the function. You can't just stay there forever, right? So make sure you include that. So here we have vowels I. And so these first three instructions are obtaining the offset. So we have the base address, A0 corresponds to I. We multiply by 4 to do by addressing. And that's in T2. So T2, we now add T1, which is the base address of vowels, and T2, and update it. So T2 is now pointing to the exact place in memory we want. And then load word, we use this a third temporary register to store the current value of T of I, and then the offset is 0 because we have a pointer exactly to where we want. So first thing we're going to do is we're going to branch equivalent if vowels does not equal 0, and this value 8 means I want to branch to 259 because that's our current value, plus 1 because that gives our PC plus 4, plus 8. So I want to go to 268. As you can see, if I do that, I go to 268. That is I plus plus, and you can see add 268 is V0. We're branching past that because V0 is branching past this and getting to our return value. So I go past this, I'm not adding I plus plus. I'm going right here, add return value, we add I, and then we add T3, which as we do every single loop, the last value of T of I is going to be the same thing as this one. So that way here, this becomes useful to use T of 3 because if we don't do this code at all, if we have I and it just immediately jumps, we still have a value of T3 automatically as vowels I. So you don't need to have more instructions there. So we break this condition, and then next thing we do is we need to see if I is less than or equal to J. Branch if equal, and we branch 5 instructions, and then set less than. If they're equal here, that means we want to do the code. And now inside the code, we need to do a load word to determine the address of sum, right? We already have vowels I, but sum is a pointer, correct? If sum's a pointer, we don't want to update sum, the variable, the T0. We need to load it from memory, but it's pointing exactly in memory to where we want. So here we just do a load word instruction, load sum into T of 5, right? And then we're going to add T of 5, which is our temporary copy of sum, plus vowels I, which we still have as T of 3, correct? We add them together, and then we're going to update T of 5, and then the next thing we do is we have to store word. So we're going to take the value, that copy T of 5, and then store it in sum 0. Does that make sense? So that's what's physically going on when you have this star sum. You have to load it. You have to load it from memory to a local temporary register, perform the addition, right, and then immediately store it because you've updated the data memory. So that's why you have load word, and the offset is 0 because the pointer is pointing exactly in memory where I want. So you don't need to do any shift left logical or anything like that for this type of integer pointer. Does that make sense, the difference between that and an array? The array is where you have to do the offset. So then here we do an add I for I++, A1, A1, and 1. And then jump 256 would be the case where since we have a while loop, we need to go back to the original instruction in the function. So that becomes this value. 268. We're taking this return value and we're adding A0, which is the value of I, or that should be A1, and then T3, and then storing it in V0 so it can be returned. And then the last thing we need to do is return to our main function. Does that make sense? a lot of sleepy looking people right now. I should call this NyQuil. Okay. Yes.
On step 263,
Yeah.
instructions, is T5,
T5.
Is sum?
T5, yeah, we're going to load sum into T5. So here in the problem, the pointer to sum is in T0, right? So we can't just add T0 because that's not the actual value of T0. T0 is telling me where in data memory it is. So if you add that, you're not changing the value of sum, you're changing the pointer to sum. So what you have to do, and since it's not an array, it's just a pointer to an integer, we're pointing exactly where we want. So you don't need to do any offsets. So you don't need to do any shift left logical, you don't need to do any of that. We're pointing exactly where we want. So T5, 0 of T0 means that integer value is 0, and we're going to be adding that actually, the next thing we're going to be doing is going into, we're going to start section 5 here in a second. I'll be telling you physically what's happening here. So to be answered in about 5 minutes. So
line 268, that's supposed to be A1?
Yeah, because it's I, not J.
Mm-hmm.
Okay, so that's the end of section 4. Section 5, we're going to be going into what's physically going on in memory. So if you recall, I had this stored program concept, and specifically where I talked about TGO 1.25, we talked about repeated use of registers or these fast local copies, right? And then we want to use data memory only in instances where we absolutely need it. In the cases where we have the non-volatile memory, it's slower, or if we have a pointer to a register like we just had with the sum variable, or we have arrays, at which point we want to try to load as many copies of elements into the registers as possible. And we're going to be going into something called the idea of the principle of locality. And the idea is that if there's two types of locality. There's temporal and spatial locality. And principle of locality is that elements in memory tend to form clusters as the operating system and the program. If you find something in memory, an element nearby is probably going to be in the program. So that's spatial. An element close by, if you use an element, then elements close by are more likely to be used immediately. And temporal locality means that if you use a value in memory, that means you're probably going to use that element again. And that just makes sense because you don't want to just have a register where you do something once and that's it. You're going to often do multiple things to that same copy of the variable, correct? So that's called temporal locality. So the whole idea is that we're trying to reuse these registers as much as possible and only do load stores when we actually absolutely need to. So here's a specific breakdown of the difference between memory and registers in MIPS. Specifically, access to registers is faster. As we know, we have the immediate values. We're going to use registers, not memory, because the memory is slower. You know that MIPS has 32 registers. This results in fewer pipelining delays. Now, what this means is that if you go to where we talk about levels of cache. So let's say I go to data memory, and the first level of cache doesn't have the element I want, then I need to go to the second element. If that doesn't have it, I need to go to the third level of cache. If it doesn't go to the third level of cache, then I need to go to the further in the memory hierarchy where I have like RAID and disk arrays and elements like that. And the further you go, the longer it's going to take. And we're going to be going over examples of this. Registers are dual read, single write SRAM, as we've discussed. Memory is single read, single write DRAM because you're only going to be loading or storing from the data memory at any given moment. And so TGO is specifically the definition of byte addressing, which we've discussed a lot already, but it means that the index points to a byte of memory. And so TGO 5.3, which is very important because now we're actually physically going on into the details of what's actually going on when we're doing all these memory saving memory or accessing. So the first one, so there's 5 parts. There's immediate addressing, register addressing, base addressing, PC relative, and pseudo addressing. So immediate addressing, the operand is a constant within the instruction itself. So add I, branch equivalent, is just stored in a 16-bit value immediate, right? Register is the second type of addressing where the operand is in the register itself. So here we have a 5-bit value in the instruction. We do our 5 to 32 decoder, and that allows us to select a specific register which has the stuff we want. So that's just the operand here. The third is called base addressing. Base addressing, and this is the answer to your question from earlier. Base addressing is what we do when we do load word and store word operations. So we take RS, if you recall, in the register transference language, it's RT is equal to 0 RS, right? So here's what's physically going on. We take the value in RS, so we have, from the instruction, we have to take the 5-bit value, decode it from 5 to 32, right? That allows us to select a 32-bit value from the register. This 32-bit value right here, where the hand is, that is the base pointer to the array. That tells me exactly where the array starts, right? Now in the load word, the 16-bit immediate value is our offset. Right? But since we're doing a 32-bit ALU, the first thing we need to do is we need to sign extend it. So we're going to sign extend it, so it's going to go from 16 bits to 32 bits. And then we take those two values, we add them in the arithmetic logic unit. So we have our physical pointer to the base element of the array. We have our offset, which tells me exactly where I want to go. We add those together, and that tells me exactly where in data memory I want to be. So that's called base addressing, because we have the base element in this register here. The next thing is called PC relative addressing. So we have, what time is it, 10:25? Our immediate value, and we have the program counter value. So the program counter, if you recall, like 256 or 263, like you were asking about earlier, this is the actual value that we're pointing to in the instruction memory. The first thing, we actually have a physical adder. Now this is why I wanted to keep just the adder separate from your ALU. This is why I had you do 2 separate problems. Is because there's actually going to be 2 other physical adders in the data path that you don't want to do add sub. That's unnecessary. So here you just have an 8-bit adder, and you're going to hard code the value 4 in here, because now you're just incrementing to the next instruction. So if there's nothing else, this is just going to go around and go to the next instruction. But if we have PC relative, that means we're branching. So we have the place I want to go to, the number of instructions I want to branch, right? Then I sign extend it, so now we're up to 32. But I also have to account for the fact that we're doing byte addressing. So there's going to be shift left 2 here. This is why you guys are doing a separate shift left logical instead of just putting it to the ALU. So now you have adders, and here's your second adder over here. So I've added PC plus 4. This is the next instruction. Then I have the number of instructions I want to branch past. If I add those together, I now have 1 plus the number of instructions I want to branch past becomes the instruction I want to be at. So instead of using the ALU, which needs to do other things, we have 2 physical adders in our data path to calculate our branch address, and then this comes back around to the instruction memory. So this is what's known as PC relative addressing. And the last thing is pseudo direct addressing, and this is what is done for jump instructions. So in this case, for your J-type instruction, you have your 6-bit opcode and then your 26-bit jump address. Now you have 26 bits, but the instruction we want to point to is 32, right? So the first thing we want to do, since we're doing byte addressing, is shift left 2, correct? So now we're at 28 bits. So we need these last 4 bits, right? We're 4 bits short. So we're going to take the PC plus 4, right? And then what we're going to do is we're going to do something called concatenation. Does anybody here not know what concatenation is? Okay, so we got a number of people, that's fine. Concatenation means you take an element, a portion of an element, and append it to either the front or the back of a different element. So here we have two elements. We have our 32-bit PC plus 4 value, right? And then we have our 28-bit jump address. So what we're going to do is we're going to concatenate. We're going to take the 4 most significant bits of the program counter, and we're going to put that to the front of the jump address. Because what's going to happen is 32-bit instructions mean you could potentially have 2 to the 32 instructions, right? Which, if you have that many instructions in your program, you need to really reduce your code size by many much. Okay, you don't want to have 2 to the 32 instructions. That's insane, especially at this level. So, what that means is that whatever those 4 bits there for the program counter, those 4 most significant bits, your jump address is probably going to have the exact same 4 bits. MIPS guarantees this at the compiler level. Therefore, and this symbol here, this circle with the up and down line here, for those of you who are looking on video later, I'll put the hand right next to it. This symbol here, this means concatenate. So we're concatenating the 4 most significant bits. We now have a 32-bit jump instruction, and then we're going to the instruction memory. Yes?
What happens if we try to pass it without concatenating?
Without concatenating, then you just have a 28-bit instruction, and then you have 4 undefined values going into your instruction memory, and then you get U's all over the place. Yes?
We shift left 2.
Mm-hmm.
But before that was like multiplying by 4, right?
Yes.
So we go from 26 to 28.
Correct. That's the number of bits.
Okay. Oh,
yes.
Okay.
Yes.
Okay.
Yeah. Oh, yeah.
That's
I should be
bits.
clear.
Okay.
26 to 28 is the length
Yeah.
of the instruction. So if you remember from the J-type topical guide objective, we have the 6-bit opcode and then 26-bit jump address here.
Yeah.
So now we need to turn that to 32. So it's 26, shift left by 2. We now count for byte addressing. We now have 28. Concatenate the 4 most significant bits. We now have a 32-bit jump address. And then, to address Andrew's question, we need to ensure it's 32 bits because we don't want to have undefined values. And this is that's tying to your question earlier. That is why at the lower levels I've been so adamant about making sure that you're testing, because as you're putting your final project is going to be putting all these pieces together into a data path. And if you're testing adequately at these lower levels, then putting the pieces together just becomes easy. And so 5.3 is a very good exam type question. In fact, when I was at USF, 5.3 would be just one slide, and that would be the thing that the professor would put in to try to sneak on everybody. So, how do we do this in VHDL? So here, the first one I want to talk about is pseudo-direct. So we have our 26-bit jump address, because we have 25 down to 0. We have a 32-bit PC in, right? So in this code, I've assumed that we've already added 4. And then jump out is going to be our 32-bit value, right? So I have a in-between signal that I've initialized as all zeros, so it's going to be 28 bits, right? So here, what I've done is I've taken my 26 down to 2, right, is just going to be our 25 down to 0, and then you can do 0, 0 like this. You can also use a shift left by 2 here. You can use your shift left logical and insert 2 to do the same thing. And then the concatenation is just 31 to 28 just becomes PC 31 down to 28 after 10 nanoseconds. Because I'm putting in, I have a 5 nanosecond delay for shift left by 2, and then I have a 5 nanosecond delay here for mapping these in a buffer, right? So then, since this is just goes straight to the PC, I've had it 10 because 10 is 5 plus 5. And so this ends the process. I have a simulation. I have two instructions here where I have jump address in the PC. You see I've specifically made 1101 as the most significant bit of the program counter. And then I have a wait here again, 1101, and then I have another jump address. So here in the simulation, we have the 26-bit jump, and after a slight delay, 1101 here is here, and then if you can see, it's 1101 are the four most significant bits. As you can see, they've been shifted by 2 because we've done byte addressing. So we've shifted by 2 and then concatenated the four most significant bits, and it works again for this level. Does that make sense? You see how that physically works in the VHDL and how we're doing that to actually calculate the jump address? So for PC relative, again, I've already assumed the adding of the PC plus 4, and I have immediate value in, that's our 16-bit value in. Now, this is going to be a little bit of an I believe button at the moment here. I'm outputting sign immediate of the sign extend. So for PC relative, you have the sign extension and then you have the shift left 2. But if you look at, actually this isn't an I believe button. I've told you enough to explain it. Here, you see I have the sign extended value is going to be just added to the ALU for the load word instruction. Whereas I multiply by 2 here to do PC relative. So I'm outputting sign extend this value here as well, so that way you can just put that into the ALU to do I-type instructions. And then branch address is going to be your calculated where you do the shift left 2. So I've done an add component adder here, 32-bit adder. So for the sign extension, if the immediate value of 15 is 1, then it's going to be negative, so you append all 1s. If bit 15 is 0, you're going to append all 0s, else undefined. And so your immediate SC, 7 down to 0, is just going to be immediate, so that becomes the 8 bits, right? And then branch address shift left 2 is going to be 31 down to 2 is going to become immediate SE. 31 down to 2 after 10 nanoseconds, and then we're going to append those last 2 bits for shift left logical. And then I've delayed the program counter by 10 nanoseconds because we've done everything else by 10 nanoseconds. And then in that case, I'm going to add our PC plus 4 and shift left logic, the branch that's sign extended and left shifted. Carry in will be 0 since it's added, and then sum will be your branch address, right? Okay, so this is now getting into assignment 4. You guys have already, I've given just the section 4 is assignment 3, so this is going to be due November 9th. So design and test a structural pair for PC relative addressing. Now this giant paragraph is where I describe how your data path is going to be different than the one I'm presenting in class. The one you're going to do on the exam is going to be the 32-bit MIPS data path. But you're coding an 8, I've reduced it to the 8-bit data path. So it's going to be different. The version of your PC relative, you're going to take the 8 least significant bits of the jump address here, and you're going to be going through this process. So I have 25 through 8. I call this jump address ignore. So you're ignoring that. And then all the PC bits here, I'm going to set the 4 most significant bits here of the PC here, so 7 through 0 are going to be what you're going to concatenate. In your code, in your test benches, you can assume all 0s for 31 through 8 for program counter, and 25 through 8 you can assume all 0s as well. I will not test for 1s there. Yeah, so basically this is what I've described. So now we have 8 bits. We shift left by 2 for byte addressing to get 10, right? We concatenate the 4 most significant bits. This becomes 14. And then you're just going to do sign extension by 18. So here I showed you how to do sign extension by 16. You're going to do sign extension by 18. And that's going to be your output. So for the second problem in section 5, you're going to do PC relative addressing. And this is how it's going to be different in your 8-bit data path than how it's going to be in MIPS. And then in the MIPS. So you're going to take the 6 least significant bits from the IH type instruction. You're going to shift left by 2. You're going to take the 8 bits from PC adder, right? And then you're going to add those together. And you're going to 8-bit sum on the output since you're using 8-bit adders only, right? So your sum and C out are going to come into your new branch address. 31 through 9 are going to be all zeros. So you just map it that way. Your carry out from your 8-bit adder is going to be bit 8 on the branch address. And then bits 7 through 0 are going to be your sum. Does that make sense? So this is how reducing the data path, this is how you reduce the size of the data path so that we don't have to do 32-bit adders and 32-bit shift and 32, all that other stuff. So I've added a little thing on here. Don't just copy and paste my code and put it in there because the MIPS specifications for the 32 aren't going to meet the specifications for your problem. You can copy the code, put it in there, and then modify it just by comparing the top thing from the topical guide objective and from your problem statement. So it's just, in this case, it's just modifying code, right? Okay, so it's 10:40. Next class, here I was going to show you how to do memory arrays, but I think you guys have had enough for one day. So it's going to be TGOs. Will we start 4.25, right? 4.25 through 5.3. And then in section 4, you did example question. I believe it's the 31st or whatever that Thursday is. Yeah, 4.25 through 5.3, and then you only, I believe, 4.13 example question. Okay, if you have nothing else, you are dismissed.